Now we're going to look at the convolution theorem. We have f of t and g of t that are piecewise continuous on that interval from 0 to infinity of exponential order. Then the Laplace transform of the convolution of f and g is simply going to be the Laplace transform of f of t times the Laplace transform of g of t, and that is going to yield us f of s times g of s. So instead of the convolution that we looked at in the previous video, now when we apply Laplace, it can become a much quicker, cleaner problem. So let's do some examples. So I have the Laplace transform of the convolution of e to the 2t and sine of t. So we can use our theorem, and it's going to be the Laplace transform of e to the 2t times the Laplace transform of sine of t. So e to the 2t yields 1 over s minus 2, and sine of t is 1 over s squared plus 1. And you can see how this is going to show the commutative property that I talked about in the last section. Because if I have the convolution of sine of t times e to the 2t, we're just going to get this, and because they're multiplied, I just get 1 over s squared plus 1 times 1 over s minus 2. So they're multiplied, the order doesn't matter. Here I want to take the Laplace of t squared convoluted with t e to the t. So I'm breaking that up. The Laplace of t squared times the Laplace of t e to the t. So this t squared is just going to be 2 over s cubed, because it's the n factorial over s to the n plus 1. And this t e to the t, that gives me a shift from s to s minus 1, so I end up with 2 over s cubed times 1 over s minus 1 squared. Our next example, I have the Laplace transform of 0 to t, the integral 0 to t, s times e to the negative 3 tau d tau. So if I think about it, f of t is just going to be e to the negative 3t, because I'm using that convolution and going backwards. And my g of t is just going to be x. So back to the convolution definitions, we can get this. And therefore, when I expand it, it becomes the Laplace of e to the negative 3t with a convolution of s. So the Laplace of e to the negative 3t times, oh, 5, I'm sorry. See, I'm going back, messing up my s's and 5s. This was a 5, not a s. So this gives me 1 over s plus 3, and this gives me plus 5 over s. And then one more. So again, I have the integral 0 to t sine of tau cosine of t minus tau d tau. So I'm using that definition from convolution to write really what my f of t and g of t are. So f of t would be sine t, and my g of t is going to be cosine t. So I'm looking at the Laplace of the convolution of sine t and cosine t, and do each of them separately. So the Laplace of sine t is just 1 over s squared plus 1, and cosine t is s over s squared plus 1. So those convolutions can be made much simpler when we actually have the Laplace transform, so you don't have to deal with that messier definitions.